Welcome to Fuzzy Mathematics, the Basics. In the previous lecture, we have talked about Boolean algebras. In this lecture, we are going to talk about soft algebras and optimal soft algebras. First, we will introduce the definition of soft algebras. A soft algebra is a dual lattice, together with boundedness and distributivity. That is, a dual lattice is called a soft algebra if it is bounded, distributive lattice. Next, we will introduce the completeness of a lattice. Suppose this is a lattice. If each non-empty subset of L has both a supremum and an infimum, then it is called a complete lattice. First, theorem 1. Suppose this is a complete lattice, then it is bounded. Suppose it is a complete lattice, because L is a subset of L. By the definition of completeness, both the supremum and the infimum of L exist. We write the supremum of L is 1, and the infimum of L is 0. Therefore, 0 is less than A, less than 1 for all elements A in L. That is, 1 is the greatest element of L, and 0 is the least element of L. So it is bounded. This completes the proof. Theorem 1 says a complete lattice is bounded. Next, theorem 2. Suppose this is a complete lattice. A and B are two non-empty subsets. If A is a subset of B, then the supremum of A is less than the supremum of B. The infimum of B is less than the infimum of A. We will prove the first inequality. Considering that it is a complete lattice, each subset of L has both a supremum and an infimum. Suppose X is in A. Considering that A is a subset of B, we have X is in B. Therefore, X is less than or equal to the supremum of B. Because X is an arbitrary element in A, the supremum of B is an upper bound of A. The supremum of A is the least upper bound of A. So, the supremum of A is less than or equal to the supremum of B. Similarly, we can prove the second inequality. This completes the proof. On the basis of the above theorem, we can define the supremum and infimum of the empty set. But maybe you can try it first. Suppose this is a complete lattice. How to define the supremum and infimum of the empty set? A good definition should be rational and consistent. Think of the above theorem. Suppose X is in L. It is easy to see that the supremum of the singleton X is X. Considering that the empty set is a subset of the singleton X, by the above theorem, we should have the supremum of the empty set is less than or equal to the supremum of the singleton X, which is X for all elements X in L. That means we should define the supremum of the empty set is the least element 0. Suppose X is in L. It is easy to see that the infimum of the singleton X is X. Considering that the empty set is a subset of the singleton X, by the above theorem, we should have the infimum of the singleton X, which is X, is less than or equal to the infimum of the empty set for all elements X in L. That means we should define the infimum of the empty set is the greatest element 1. Next, theorem 3. Suppose this is a complete lattice. Let A and B be two subsets of the lattice. Then the supremum of the union is equal to the maximum of the two supremums. The infimum of the union is equal to the minimum of the two infimums. We will prove the first equality, considering that this is a complete lattice. Each subset of L has both a supremum and an infimum. Using the definition of the union of crisp sets, we have A is a subset of the union of A and B. B is a subset of the union of A and B. By the above theorem, we have the supremum of A is less than or equal to the supremum of the union, and the supremum of B is less than or equal to the supremum of the union. So the supremum of the union of A and B is an upper bound of the two supremums. Therefore, we have the maximum of the two supremums is less than or equal to the supremum of the union. On the other hand, suppose X is in the union of A and B. Then either X is in A or X is in B or both. That means X is less than or equal to the supremum of A, or X is less than or equal to the supremum of B or both. So X is less than or equal to the maximum of the two supremums. Because X is an arbitrary element in the union of A and B, the maximum of the two supremums is the upper bound of the union. The supremum of the union is less than or equal to the maximum of the two supremums. Using the antisymmetry of the lattice, we have the supremum of the union is equal to the maximum of the two supremums. Similarly, we can prove the second equality. This completes the proof. The above conclusion can be generalized as follows. Theorem 4. Suppose this is a complete lattice. Let I be the identifier set. A sub I is a subset of L for all I. Then the supremum of the unions equals the supremum of these supremums. The infimum of the unions equals the infimum of these infimums. Next, infinite distributivity. A complete lattice is called infinite distributive if the distributive laws hold. Meet distribute over join, and join distribute over meet. If a lattice obeys the infinite distributive laws, the generalized distributive laws, we say that it has infinite distributivity or generalized distributivity. Next, the definition of density of a lattice. A lattice is called dense if A is less than B. Then there exists an element C in L such that A is less than C less than B. Now we can introduce the definition of optimal soft algebra. An optimal soft algebra is a dual lattice, which is dense and infinite distributive. An optimal soft algebra is a dual lattice together with density and infinite distributivity. Till now, we have talked about Boolean algebras, soft algebras, and optimal soft algebras. Let's recall the definitions of them one by one. First, Boolean algebra. A Boolean algebra is a complemented lattice together with distributivity. A complemented lattice must be bounded. A lattice is bounded, that is, it has the greatest element and the least element. Next, soft algebra. A soft algebra is a dual lattice together with boundedness, and distributivity. A dual lattice is a lattice that obeys the double negation law and the De Morgan laws. Next, optimal soft algebra. An optimal soft algebra is a dual lattice, together with density and infinite distributivity. It is dense, and a lattice has infinite distributivity. It must be complete. Of course, a complete lattice is bounded. This is the end of this lecture. Next time, we will talk about the algebraic structure on the closed interval from 0 to 1. Thank you.